Welcome to Aquanix's incremental compilation demonstration. In this video, I will demonstrate the incremental compilation feature in the ACE software that allows users to break a design up into smaller logic units so that when recompilation is done, only the partitions that have changed needs to be recompiled, leading to preservation of results and compile time savings. Before learning about the incremental compilation process, it's important that you already have a basic understanding of the ACE FPGA design software. If you need to learn more about Aquanix's tools, visit the training video site on aquanix.com. I especially recommend viewing the ACE place and route tutorial. In this training, you will learn how to break down your design with compile points for synthesis and partitions for place and route. You will also learn the steps required to achieve significant runtime savings when recompiling your design. There are many benefits when you synthesize, place, and route your design with incremental compilation. You will achieve faster and more predictable recompilation times, since unchanged partitions will not be recompiled. Unchanged and hopefully timing-closed partitions will also be preserved. This allows you to work on the changing partitions while preserving the compilation results of unchanged partitions. Faster timing closure can be achieved since you'll be able to focus and iterate on potentially problematic partitions while not wasting time recompiling partitions already meeting timing. The basic steps of using incremental compilation in ACE is specified here. First, break a design up by defining compile points in the .fdc FPGA design constraint file used by Simplify Pro. Next, enable the incremental compile option in ACE. Then run the design through synthesis. Simplify Pro synthesis will generate the project implementation partitions.prt file, which will list the partitions being created. Next, run place and route, which will compile the partitions independently. After that, for any subsequent changes to the original RTL, when compilation is rerun, only the partition or partitions that contains the changed RTL will be recompiled, while all other partitions will be preserved from the previous compilation. This minimizes the time it takes to make incremental changes to existing RTL, while also minimizing perturbations to existing design implementations in ACE. Let's begin the incremental compilation demo. Here's the design. It's a relatively small design but contains numerous modules. Incremental compilation partitions work closely with synthesis compile points. The first step is to mark the modules for incremental compilation as compile points for synthesis. In the .fdc file, the FPGA design constraints file, we have defined 9 compile points for synthesis. Compile points are hierarchical module boundaries that Simplify Pro synthesizes separately and then will be able to reuse during later compilations if the RTL for that block does not change. Instantiations of these compile points will become partitions in ACE. Note that we could have defined compile points in Simplify Pro GUI as well. Let's enable incremental compilation under Project Options. Once this is enabled, you have the option to enable synthesis auto-compile points. This option uses various heuristics to select a set of modules as compile points. These may be in addition to any compile points manually specified as constraints. Since we have these already manually defined, we'll leave this option off. With incremental compilation, you have a choice of 2 modes, Smart and Strict. Strict mode ensures that placement of locked instances in unchanged partitions are preserved, while Smart mode, the default, allows ACE to try to intelligently preserve placement in locked partitions for better design performance. We will use the Smart mode. We're ready to run synthesis now. With synthesis complete, looking at the Simplify Pro synthesis report, in the Summary of Compile Points section, you'll see a summary line for each compile point, each one corresponding to the modules defined in the FDC file. Notice for each compile point, the status is mapped because this is our first time running through this design. Let's look at the partition definition file. This file is created by Simplify for inclusion in the ACE project. It includes tickle commands that defines the Simplify compile points as partitions. Each command contains the instance and view names for each partition. Note that there are many more partitions in the .prt file than there are compile points in the Simplify log. This is because partitions represent instances, while compile points represent modules. We will need to add the partition definition file to the place and route constraints for ACE. Now we're ready to resume the compilation flow. After the run prepare step, the partition report automatically appears. You can also open the partition report in the project view under Outputs. In the summary section, you'll see the number of partitions and the number of them that were recompiled. In this case, we have 100% recompiled because this is our first path through the flow. Also listed are the number of total instances and nets and the number of them that were recompiled. In the details section, we will see a table with one row for each partition, and the columns are the various resource information for each partition. Place and route has completed. I will now open the floor planner and take a look at the partition window. Here, you will see information for all of the partitions and whether they were recompiled. Again, here everything is compiled since it's our first run. You can also enable force recompile of a partition on the next run, regardless of whether the partition has changed or if synthesis was rerun. Next, we can choose to highlight or unhighlight partitions individually. This makes it easier to view specific partitions in the main floor planner. The auto highlight feature is also available. It's very powerful to understand logical and physical connections among partitions. Placement of those partitions is heavily dependent on connectivity. In the netlist browser, you're able to see the partition that owns each of the instances. If the partitions are highlighted, you will also see the highlight color in the highlight color column. Going back to the project view, now I'm going to change the source code for one of the modules, FPU multctl.v, using a different version of the module that has a flop added. Its source code RTL is in the v1 folder. Now I can recompile and hopefully reuse most of the partitions. With synthesis complete, looking at the compile point summary in the synthesis report, you will see that the FPU multctl has been resynthesized while other modules have not. With the prepare step done, looking at the partition report, you see that the instances of the FPU multctl are recompiled while all other partitions are not. In the summary section, it shows only 4 out of 37 partitions were recompiled. That's 4.6% of instances are recompiled, while 5% of the nets were rerouted. Lastly, note the timestamp. The recompiled modules will have an updated timestamp. Now the place and route is complete, let's switch to the floor planner view. Looking at the partition view, see that only 4 partitions, the instances of the changed FPU multctl, are now recompiled. In the floor planner, most of the instances are dark yellow now, since they are of locked placement state, meaning they are part of the partitions that were not recompiled. Only the light gray instances are allowed to have their placement changed. Let's change the colors to make the changed and locked partitions more visible. We will use yellow for changed or placed partitions, and we'll use red for unchanged or locked partitions. Next, we will examine the amount of rerouting that was required to accommodate the RTL change. We will do that with fly lines. These are straight single segment lines directly connecting a net source instance and sink instance, where either the source or sink is a selected instance. In the partitions pane, select the instances that were recompiled. Then, enable the layers for selected instance fly lines. The fly lines are then drawn for the first 200 selected objects, and we can use the arrows to see the next 200 and so forth. This is helpful in understanding the effect of any placement and routing during the second path. You may see, for example, that changes in the RTL were too extensive for effective incremental compilation, causing failing critical paths with wayward placements. In that case, you can force recompile on next run for all of the partitions that were problematic. Lastly, we can highlight all the changed partitions to observe any changes in the placement of the changed partitions. We can leverage the auto highlight feature for the partitions again. To summarize, you should now understand how to use the incremental compilation feature in ACE to minimize the time it takes to recompile design after RTL changes. If you need more details, please visit the support portal at support.aquanix.com. Thanks for viewing this training.